we said that, let's say, the idea is that we have our system S, and we have a set of, let's say, ancillas that in our, let's say, basic setup, they all arrive identical to each other. They arrive, they interact through Vn for a certain amount of time, let's say. Let's call this amount of time delta t, and then they go. And then the new one arrive. And we said that, let's say we can build in Markovianity from, let's say, by construction, by saying that the various ancilla are completely correlated, they don't interact with each other, and they never come back. So once they've done what they have to do, they disappear, and we completely forget about that. And this, let's say, gave us the great simplification. Say many, but one of them was that, let's say, sigma n. So the state, the full state. No, let me say different. The system state, so let's say rho s after n collisions that we know is given by the trace over n, trace n minus 1, trace 1 of sigma n, where sigma n is the full state. This simplified dramatically because of these properties, otherwise no, simplify dramatically to epsilon to the n of rho 0 of rho 0, because our, let's say, our notation was put in the ancilla state as, let's say, part of the collisional map. And we said that this is the collisional, epsilon is the collisional map. And then what we did was to, let's say, expand epsilon, the collisional map, to the second order in delta t. And you remember, we took this strange decomposition in which we said, let's say, we said that the H0, say the free part, doesn't enter in the second order, enters only at the first, but V enters enters also at the second order. And we said, okay, this is weird, but we will motivate. And we didn't do the, we haven't done yet. Now, the last part was to, let's say, to realize that this gives us, let's say, a Limbladian formally, if you want, Limbladian representation for. Do you have a question? No, okay. For this collisional map, gives, let's say, Limbladian formulation in which, as I said, a little bit like an overkill. We said, suppose that we know everything about our ancillas. So we write this as a summation over k, pk, k, k. So we assume that we know exactly the probability. We know exactly, let's say, the decomposition of the ancilla. And out of that, we said, okay, so now we have the, let's say, we can get our equation in the form of a Limbladian equation, like minus I HS plus trace over n on V n eta n over rho n minus 1 plus, and this was, let's say, that, I mean, as I said, this is the system Hamiltonian. This is what Jamir called in his lecture the Lamb fifth, that again, another name that I guess has to, okay. You know, we were making names that look like something else. Lamb shift, one think, okay, maybe no, it's the guy, probably the name of the guy. Sum over k and k prime. L K K prime rho n minus 1 L K K prime dagger plus say minus 1 over 2 1 over 2 L K K prime dagger L K K prime rho n minus 1 an anti-commutator. And that's it. And LKK prime was defined in this way. LKK prime, which are our jump operators, are given by square root of PK, square root of delta T, times K prime Vn A. So it takes, let's say, the matrix element of the interaction operator over the ancilla states, the ancilla, the states entering in the decomposition, in the spectral decomposition of the ancilla state. It takes the square root of the probability distribution of the ancilla, and you get this. Okay, so this was, let's say, the end part of yesterday's lecture. There are, yeah, please.
Yeah, wasn't there delta T in that second part?
No, I decided to reabsorb delta T in the definition of
Okay.
yeah. But yes, there is. Just reabsorb there and you don't see it. Okay, other comments? Okay. Good, okay, just one thing, I mean, here it looks a bit weird that, let's say, we have KK prime and we have, I mean, it looks asymmetric between K and K prime, and indeed it is, because you remember, well, if you do the computation, you see that this guy is entering, let's say, by, I mean, K prime is the index entering in the trace, and K is the index entering in the state here. So when I put the state, I have rho tensor, let's say, PK, K, K, and here I'm sandwiching because of the trace, I'm tracing with K touch. So it is asymmetric. Even though at the end you do a final sum, so you get all the, I mean, you get everything. Okay, so now, as I said, the next part is that this is definitely an overkill. You don't need all this information. So you, when I say all this information, you don't need all this part. You need less than that. And our goal is to see that, let's say, you can get the equation of motion by just knowing, let's say, the first and the second movements. So this is, let's say, the goal now. So to do that, we need to do a step that Jamir did in his lecture. Yeah. By, let's say, let's assume it's very reasonable, so there is nothing to assume. But let's say let's make explicit. Let's say not assume, make explicit the form of Vn. So in general, without any assumption, we can say that we can write this as a summation over an index. I don't specify right now because this is highly, say, model dependent. We will do a couple of examples to see. And this guy is a system operator, and this guy is an ancilla operator. So we all agree that this is a super general, let's say, decomposition. I haven't put any constraint. This is the most general form. Okay. Now, out of this, let us define the moments. So let's define, let's say, B mu, which is the trace, much fantasy, the trace over n of B mu eta N, and B mu, B mu. So instead of, let's say, here I'm not assuming the knowledge, the precise knowledge of the state of it. I'm just assuming that somebody has given to me this guy and this guy. And now the idea is that we will, I mean, it's a very easy computation. We will show that these two informations are enough to recover the full equation that I wrote before. So to do that, essentially what we have to do is to start to compute these guys. And yeah, please.
It's BB as
Sorry. Thanks. This was the complaint, right?
Yes.
Okay, good. Okay, so let's compute the guys. I mean, really, let's say simple exercise. So let's compute, for example, this guy, raised over n, Vn, eta, n. This, of course, becomes raised n summation over mu, g mu, b mu. No, well, vabbè, here. A mu, eta, n. Now here I can use some trivial properties, so I think you all agree that they can bring out G nu and they can bring out A nu because they act on, I mean, G nu is a number. And A nu is acting on the system, so it's nothing to do with the other. So we see that this simply becomes summation over mu, G nu raised over n, B mu, eta, and A mu. So all in all, we see that this will become summation over mu, G mu, B, A mu. So we see that for this term, the first moment is enough. Now we can redo exactly the same computation. So I mean, this is a really simple exercise, and we see that, for example, well, let's write all of that. Trace Bn rho and eta and Bn. This simply becomes wait, what is this guy? Ah, yeah, sorry. I went back. Okay, yeah, sorry. My mistake. I mean, I went back to the original equation. Do you have it, or should I write it? I mean, the original equation, do you remember? Was it, instead of involving, let's say, already the L case, was involving terms like this. It was involving terms in which we were sandwiching the full state with a V on the left and a V on the right. Is it clear to everyone? Because I went back by one formula. Is there anybody that is not convinced? Everybody is convinced?
Yes.
Okay, good. Okay, so no, you're not.
you can move on and I can jump. It's okay.
Okay. So, I mean, it was the moment that you said, okay, the next step is dividing by delta T.
Yeah.
That was the equation. Okay, so we had terms like that. So this term, I mean, simply become summation over mu and mu of G mu, B new, B new, A new, rho n, new. And so we see that here again, all the dependence on the initial state has collapsed to the second moment. And by the way, this is exactly in the spirit of what Jamir was putting, you remember, was putting some expectation value over the buff of the various operators acting on the buff. This is essentially the same thing. The point is that here the buff, it's not the collection of complicated stuff, it's just one single ancilla that is interacting at that moment, but it's really the same object. And then there is an extra term that was given by trace over n of, let's say, this way, Vn squared, rho n minus 1, theta n plus, and again, this, again, without too much fantasy, goes back to something that involves only B nu. So we see that everything can be recast in that form, and we can end up with this much nicer equation. But let's go this. Okay, so we end up with this much nicer equation that looks d rho n over dt equal to minus I hs plus hs prime rho n plus ds rho n minus 1, where these objects, as we said already, they are hs prime equal to g nu, b nu, a nu, and ds on rho n minus 1 is given by summation over mu and mu, gamma mu mu, that I define in a moment, b mu, b mu, a mu, rho n minus 1, a mu, plus minus 1 over 2, a mu, rho n. And finally, our gamma mu mu is given by g mu mu g mu delta t. Okay, so this equation is exactly the Lindbladian equation that we got, which with a completely different, not so completely, but okay, different approach, and in a different formalism. I mean, okay, there are a few comments to say. First of all, if you want the coupling with the buff, this again is just repeating what we already said. The coupling with the buff is coming in two ways. One is unitary through this term, and the other is dissipating, so non-unitary through this term. So the buff enters in two ways. One is completely unitary, so with just this part, the dynamics would remain unitary, but already fill the buff through this term. But then when you turn on let's say when you turn on the buff, if you have a second moment, you get the dissipative part as well. So for example, one, let's say, possibly interesting, let's say, way would be to see if there are interesting models for which the second moment vanishes, so you can maybe look for a dynamics that remain unitary, but is coupled to another one, to another system, for example. But okay, in general, the dynamics become completely, let's say, dissipative given this other data. Now, the other thing, okay, what is another feature that should, let's say, make you a little bit unknown? No,
The strength of the interaction depends on
Eh.
delta T. So if
Eh.
you want to make it delta T small, and you vanish the interaction.
Exactly. Okay. This is really a point that should, okay. Again, depends a little bit on your mindset. Let's say that you are modern. Let's say that
Contemporary.
you pretend to be modern and you pretend to say that let's say these collisional models are relevant in quantum simulators or other things like that. In that sense, you could say, well, getting a delta T small, but fine, it is perfectly legal. So my delta T is something that is not, let's say, just, how can I say, an artificial way to reproduce a continuous dynamics. So I don't care about going to the limit of delta T equal to 0. Delta T is a physical thing, is a physical object. So this is a super well-defined equation for a system that behaves like a collisional model. As far as I know, the only example is again the micromeasure. And indeed, in the micromeasure case, you don't care at all about this problem. But now, historically, collisional models have not introduced in this way, and as we will see, they've been introduced in order to get another, let's say, formalism to treat actual physical systems. As you said, in actual physical systems, time is minus. Okay, we can maybe discuss about that, but okay. At this level of precision, we can say that it's continuous. And so we should worry about that, let's say, dissipation disappear completely because there is a delta. So, and even, so let's say the strength of the dissipative part depends on delta T. So in the limit delta T equal to 0, the dynamics become completely non-dissipative. So now what? Yeah, please.
Something that makes me curious is this is a completely different approach to unraveling the Lagrangian form, as we discussed it yesterday.
Yes.
And also with these monitored quantum systems, that is a
monitor. Monitor it.
Yeah.
Okay, monitor it maybe is slightly different.
Yeah. With monitored quantum systems, you can also unravel the Lagrangian form, just taking the average in each stochastic trajectory you have. But that is not my point here.
Okay.
My point is that in this kind of approach, you can see some of phase transitions when you move the strength of the dissipative part. So do you think that if we can have similarities in this case, like quantum dynamical phase transitions, just tuning this? Because with delta T seems a little problematic.
It is. Again, this is important to stress. It depends, as I said, on your mindset. If you have an experiment that can throw one, let's say, qubit or one system and interact for a finite time, it's not. But as you said, if you want to use this machinery to simulate something different, this is important, and we are going to work on that now to see how we can make things well-defined in the delta T equal to 0 limit. Now, monitoring quantum circuits is what you mean, right? And the phase transition that you mean is what people call the entanglement phase transition, right? Something like that.
Yes.
Not sure it's exactly the same thing, right? Because
No, I don't think it's the same.
Exactly, because there is a question. The monitoring actually could reach the same. Okay, is exactly your question. And to be honest, I don't have a good answer right now, because I'm not an expert at all about monitoring stuff, so I'm not. Let's say I'm not answering for something that I know by heart. That is a little bit different in the sense that you don't have an ancilla that arrive and then you trace out. It's more that you let your system evolve and then you do a measurement and then you let it evolve again and you do a measurement.
Random times.
So if you want, the common point is that you have a circuit dynamic and you have a well-defined delta t, which is that if you want the time between one measurement and the other. So for this, I see a similarity. You don't, okay, we have, by doing weak measurement over the ancilla, you are asking too much, I'm sorry. I absolutely,
Just
yeah, you have a comment,
Let's make
please.
a comment. You spoke about the mindset, for example, from my perspective.
By the way, so, because we didn't check until now, people in the chat can hear the questions by the audience or they just hear me, no, right? It's not, you can hear everybody, right?
I think they can. I saw the YouTube video yesterday.
Ah, okay,
I
you
could
could, okay,
listen.
perfect,
Yeah.
okay.
No, I was just making a comment about the mindset.
Mm.
For example, in my point of view, more of like a quantity of information for communication. The dependence on the delta T makes a lot of sense because when we study, for example, the loss of information due to noise,
Mhm.
noisy channel and so on, it makes sense that like depending on the time, you are actually reducing the amount of like collisions or absorption events that like the photon
Mhm.
can suffer, and each of these events will add a phase on it. So
Mhm.
if you think even like in classical physics, you're thinking about like impulse, which is
Okay,
force time.
yeah.
So the amount of momentum in
Mhm.
or phase that you are giving to the photon is associated exactly with the time.
Okay, so,
So it makes, for me, it makes more sense that.
okay, perfect, nice to see. For me also, because I started to learn actually about the collisional models just a couple of years ago when I was studying the micromeasure. As I said, the micromeasure is really that you have, I mean, in physical term, you have a cavity in which you put an electromagnetic field and with just, let's say, monochromatic, let's say. And then you pump one atom at a time, at each, let's say, one atom at a time inside the cavity that interact with the field and then goes. So there it's an instrument that by definition has a well-defined delta T, which is the time that the atom pass inside the cavity before leaving. For that, this is exact. If you want, the approximated case would be the dt equal to zero limit.
You have super radiance in this kind of system also.
Yes, I don't think so, because as far as I know, the super radiance is okay. Here we have two real experts about the super radiance. The guy is checking the phone, but he is the super expert. You are the super expert about super radiance, right?
Not really.
Anyway, as far as I understand, the super radiance is a phenomenon in which you have many qubits and one electromagnetic field that cause, let's say, a collective effect on the qubit.
Oh,
Here, instead, the qubits are coming once at a time,
Yeah.
so I don't
you
think so.
don't have collect.
But ask him. Okay. So far, so good. Okay, so now are the other comments? Good. Okay, so now our goal would be to, let's say, discuss what to do for dt on zero. With the idea that what I mean with this is that we want to do something that keep, let's say, the dissipative part non-trivial, while now probably before doing that, I want to do an example such that we, let's say, we get accustomed to the formalism, and then we will do so. Let's say first let's do a small exercise, and then we can move to this discussion. Okay, so let's go back to our old friend, which is the old qubit collisional model. And let's put for simplicity, let's say GZ equal to G. So our V become, I was putting minus or plus G, okay? Sigma plus sigma minus plus sigma minus sigma plus G. Okay. And okay, so essentially we want to write this equation for that particular case. So the indices new entering here, I mean, obviously they are plus, minus, and z, right? These are all the indices entering here. Let's say it's 3. Then we have that, let's say the A are this. So we have A minus equal to A plus dagger equal to sigma minus.
Sorry,
Yeah, please.
the GZ is times the 20.
Sorry. No. Thanks. Sorry.
It's sigma ZZ.
Absolutely.
Yeah.
Sigma Z. Sorry. Thanks. This, okay, and AZ is equal to sigma Z. And then we have B minus equal to B plus, dagger equal to sigma plus, and okay, easy is equal to sigma Z. Okay, and again, as we did yesterday, let's assume that our eta is arriving in the state 0, 0. So with this, let's again do a small exercise. Let's compute B mu. This is the trace over n of B mu 0, 0. And so what do we get?
Oh, 0. Easy can be PM1.
No, bad. We
Yeah,
said that the
minus
initial
1.
state, so it's -1. All convinced? Okay. And then, okay, simple again. B mu, and the trace over n of B mu, 0, 0. And here we get perfect. B plus, B minus.
Zero.
One of the two become 1 and the other becomes 0, right? Because
Oh,
well,
okay.
now it's a little bit confusing.
Yeah,
B
because
plus
that's
is
the
the
die.
sigma minus. So let's say I would say, yeah, this one become 1 because B minus is actually sigma plus. I mean, it's just because to the center side the minus here you have
I was confused.
it's a triviality, but okay. So one of the two become 1 and the other becomes 0. Okay. So the final equation become well, okay, okay, so we can just compute. So let's say HS prime in this case become minus G sigma Z. So this is the deformation of the Hamiltonian part entering here. And the dissipator take this form. So ds over rho m take this form, let's say gamma, which is here it's visible, G squared over delta t. and here we get sigma minus, rho n minus 1, sigma plus, minus 1/2, sigma plus, sigma minus, rho n minus 1, rho n minus 1 with the plus, plus gamma sigma z, rho n minus 1, sigma z, minus rho minus 1. Okay, so this is the final equation. We will see in a moment that this is an interesting equation. But still there is a, okay, so now we are ready to go to the point that, let's say, we were emphasizing before. So here we see explicitly that all the dissipation depends on delta t. So when delta t becomes small, no dissipation at all. What can we do? What can we do in order? I mean, let's go with the trivial solution and then let's see which problems arise and how to fix and so on. So to avoid this problem, we can say that, I mean, the trivial thing is to say that G is delta T dependent, right? If I say that the coupling is dependent on the interaction time, is a wager. So in principle, you could say, well, I simply say that my G become a G, say, of delta T, such that this is, let's say, the square root of, let's say, gamma, I mean, a fixed number, divided by delta T. In this way, this.
Something that we have already the Link-Gladian for equation.
Repeat.
It's something that we have similarity in the Link-Gladian equation because you need to divide by the square root of n.
Exactly. So it's,
Yes.
I mean, it's a signal that we are on the right track.
Yes.
It's a signal that we are on the right track, but is this enough? Who votes for yes? Nobody. Who votes for no? Nobody. Good. Okay. Well, let's avoid politics again, saying that people don't go to vote anymore, at least in Europe. But okay. No, come on, let's make proposal. Who vote that this is enough to say, okay, at least formally I solved the problem. Let's say formally. Let's avoid physics for a moment. Who say that this is enough at the formal level to say we solved the issue? 1, 2, 3.
I can't see any problem already.
Okay. So, okay. Are there people that say no, it's not enough, even at the formal level? Typically, when I ask, Francisco knows, when I ask these questions is because the answer is there is a problem. So. You see a problem?
More or less, like I think it's formally solved, but practically you need to break it down into like a basis for the like.
No, it's more trivial. No. The problem that I mentioned is way more trivial than. Okay, it's a triviality. In the equation is entering also this guy. If I do this redefinition, what I get is that goes to infinity.
Yeah.
So if you want, the dissipation become finite, but I get an infinite contribution from there, so nothing. So this is not, even at the formal level, this is not a good way. So we need to do more. And this is, if you want, I think this could be a sort of no free lunch theorem, let's say. We say that this formalism is very flexible, allow you to essentially do whatever you want, put ancilla in whatever state. This is all true until you take the formalism for what it is. So a formalism in which delta t is a discrete stuff. If you want to go to something that makes sense in a sort of real physical picture, all this freedom become problematic. And here we are seeing that there are no, let's say, simple solution. So in order to really solve this problem, we have to do something more. And we have to, let's say, play a little bit with our other ingredients like HS. And what is another ingredient that we can play with?
Sorry, just something. You say that you are trying to get to a real physical system by bringing the delta T to 0.
I'm saying a slightly different thing, like this is an intrinsic, it's essentially what you say, Chuck. This is an intrinsically, if you want, stroboscopic dynamic. So it's a dynamic that is going discretely, like you have that, then another, then another. This is can be physical in an experiment, but it's definitely not the way that you imagine that the system interact with another system if you let them free and let interact. So if you want to make, let's say, contact with the equations, even if you want to make contact with the Lindbladian equation that Jamil wrote yesterday, that was a genuine derivative of rho with respect to t. So it was a genuine limit to dt equal to 0. So if you want, in a sense, if you want to go beyond the formal similarity to something that is really the same thing, not the formal similarity, the intuitive similarity to something that is really the same thing, you have to promote this to a real derivative, right?
I more or less grasp what you're saying. I just have a little lack. I think I have a lack of understanding of what exactly is delta T, because
delta T is the time that the ancilla number n interact with the system before leaving the stage to the next ancilla. You see that this is a very artificial construction.
yeah, but at the same time, when you talk, like when you put that idea that is the ancilla, the interaction time needs to be finite. Like it's not just pop.
No, you can think that you want to define a limit in which the time at which the ancilla interact becomes infinitesimal, and infinite many ancillas interact in a finite time, right? So you can think like a sort of a double limit in which n goes to infinite and delta t goes to 0, such that the role played by a single ancilla becomes the role played by many ancillas that sequentially arrive.
I understand that, but there's a limit of n going to infinity, but you have a range where my ancilla will interact with my target qubit, and that ancilla will have a speed smaller than the speed of light. So that's
okay.
Space range.
Okay, here, let's say, here we are totally non-relativistic, so we can assume that the speed of light is infinite, right? Otherwise, you have to start to think about relativistic effect, and I'm not the right person to talk about that. So let's assume that speed of light is infinite, but in any case, let's say in any case, I think it's disturbing that the actual physical behavior of your system depends on the discretization on time. Right? We are going onto the philosophical, probably.
It's not exactly philosophical. My thing is, I understand that there's a continuous evolution while the ancilla.
So, sorry, why? Let me be provocative, but in the good sense. Why you didn't raise the same question when people write the Schrödinger equation? Also, there you could think you cannot. You need to interact. Is how, let's say, calculus work, right? I mean, you look for a limit in which the interaction time becomes smaller and smaller. But again, when you do, for example, when you do let's say oh my gosh, the time ordered evolution operator, right? There you are, what you are thinking is about a meshing of the time axis in which each mesh becomes very small such that you can approximate, let's say, exactly. And you assume that you can do this in a well-defined way such that the final result doesn't depend on the way in which you define to do this meshing, right? That you can, let's say, send this mesh into infinity and things remain well-defined. I think here we are exactly saying the same thing.
Now I understand better.
Good. Other? But yeah, sorry, I didn't want to be provoked. I wanted
Yeah,
to
it
say
worked.
that in order
It
to make the comparison with something that you don't complain about, because we are doing exactly the same thing.
No, I understand. It worked. I
Okay.
understood, but
Others? Okay. Okay, so let's do this before finishing, and then we do the last hour for the final part. Okay, so here, as I wanted to say, let's say the price to pay is coming out. We cannot keep this flexibility if we want to do a limit at dt equal to 0. If you want let's say the problems are arise. So we have to play with other ingredients. One, as I was saying, is the Hamiltonians. And then there is another ingredient that we can play with. Proposals?
Can you re-ask?
Yes. I mean, I was saying, in order to have a well-defined dt equal to 0 limit, trivial things like setting this are not enough. They need, and as you correctly, yeah, you have the answer. But let me finish the question for him, and then you give the answer. As you said, sending the coupling constant to infinity is on the right track, because it's what we saw also yesterday, but it's not enough. We have to play with other ingredients. One ingredient is this Hamiltonian, HS, and there is another ingredient. What is the other ingredient?
the other ingredient is the strength of the Hamiltonian. You need to like, it's going to, if
You are changing the Hamiltonian.
yeah,
You are
need to-
paraphrasing what I said, like, no, there is another ingredient that I have in mind. The other ingredient that I have in mind is the oscillar state. It also plays a role because it is entering via the moments. So I can play with the oscillar state, and this we will see that this has an important counterpart when you go to real physical
Like,
systems.
since you know the probability, the mixture state of the oscillator, you can put the delta T on the.
No, I was saying that you can replace the initial state with another state,
Yeah, but
such that
you are suggesting that you can put the time dependence on the oscillator state, something like
also,
like.
and it
the
looks very
probability-
weird.
Yeah,
It looks very weird, but it's not. We will see.
okay.
No, actually, we will not see. We will see the simplest example, and then I will convince you, hopefully, that otherwise we will discuss that this is okay. Anyway, let's do first the simple solution. So this no, okay, but everybody has this written on their notes, so we don't. So, first solution. Play with the Hamiltonian. So, a very first way to solve this problem is to simply send GZ equal to 0. Because, okay, here is now confused, but secretly here, there was not G, there was GZ. So we see that, let's say, GZ equal to 0 and G equal to, let's say, square root of gamma divided by delta T, and theta equal to 0, 0. It's enough to recover a well-defined DT limit with a non-vanishing dissipatory part, because this part died. And by the way, the equation that you get, maybe you know, and if you don't know, I'm sure it will be covered by one of them. I put the pressure, right? But, yeah. So this equation
Now I'm a bit confused
please.
because the coupling that makes sigma z exist in the equation defines.
Remember, the original
Yeah,
Hamiltonian, the original Hamiltonian had let's
Yeah,
say,
yeah, yeah, yeah.
GZ
Yes, yes.
over G. Let's say, cioè,
No, yeah.
so you can say I change, cioè, I take, if I want to, if I
Yeah,
want,
it's not maths anything, I'm sorry.
you agree, right?
Yeah.
Okay, good. So if you do, and you compute, you get this equation. Now, does anybody have seen this equation in the past? What is that?
It's the phasing.
Is I would say the spontaneous decay of a two-level
Yeah,
atom
yeah.
in a path. So we have seen, say, I think interestingly, that with this very weird and very artificial formalism, by starting with all the ancillas in the vacuum state and by removing the GZ part, we end up with a well-known equation in quantum mechanics, which is the, let's say, the decay of a two-level atom in a path. So this is already, let's say, another remark that we are on the right track. And now let's see, by the way, are you gonna cover these cases, right? Probably somewhere. No, too simple, probably. No. Oh,
No, PFT construction.
okay.
And in the tutorial, there will be like the defacing.
Okay, so yeah, good. Okay. However, let's say, again, this is one solution. Let's look for another one. Now, another one, maybe more interesting, would be to play with ancilla. So let's say, let's now stick with these two. Like we remain with GZ equal to 0. We remain with G equal to, I mean, a diverging stuff. But let's play with the ancilla state. So on top of that, keeping them, let's now assume that our ancillas are, okay, they are cubics, of course. And let's now assume that the ancilla state on top of that is given by eta equal to chi, where chi is 1/1 plus alpha n delta t squared. Zero plus alpha n square root of delta t 1. So we take this state for the ancilla. And now let us compute sigma plus equal to sigma minus star. So the moments, the first and second moments of these guys. Now this, it's a very simple computation. We just need to pay attention to, let's say, to keep only at the order square root of delta t. So we have to compute this beast and keep only at the order square root of delta t. So if you do that, you see that this guy, they both goes like alpha n star square root of delta t. And moreover, the other moment, sigma minus sigma plus, it goes like 1 at the order that you want to keep.
Right.
Yeah.
You should have, is delta t squared or delta?
This is delta t squared. Is it, I think, no, wait, no, sorry, you're right. The square is here and this is delta t. Yeah, sorry, it's just the normalizing factor. Yeah, thanks. So this is, and also sigma plus, sigma minus, this would be non-zero, but at the order, let's say the first contribution that you get is of order delta t, so this is effectively zero. In the delta t equal to zero limit, disappear. So now you do exactly the same computation. And for example, if you assume that alpha n is, let's say, modulated in time in this way, where a is a constant now, so let's say, well, it's a constant, e to the minus I omega n t, you end up with another very famous equation, rho dot equal to minus I d a e to the minus I omega L t sigma minus plus e to the I omega L t sigma plus rho n minus 1, no, rho, because now it's positive, plus gamma sigma minus rho sigma plus minus 1 over 2 sigma plus sigma minus. Yes. And this is again another well-known equation. I think is called block equation because it let's say describe again a two-level atom that is, let's say, will tend to, let's say, to decay to the ds site in the ground state, but it is modulated by an external field. So once again, we got a very well-defined equation and very well studied via this method. So if you want, this gives an idea on how you can use, let's say, collisional models in order to describe, let's say, physical situations that you can get with other methods. The idea is that the guiding principle is, maybe I'm exaggerating, but the guiding principle is that you should look for something that is well defined in the delta t equal to zero limit. If you do it, probably you are getting a reasonable equation in the real world. Otherwise, you can claim that you have your reasonable equation in the, let's say, discrete world that, as I said, is becoming real to a certain extent, at least. Now, before concluding and going to the coffee, let me also ask you one thing. Do you see now why that weird expansion was not so weird? Do you know which weird expansion I mean? Yes,
Distribution theory on only the
right. Do you see
part.
why now? Yes.
Because if set that G equals to 0, so the
G goes to infinity, right? We are taking a G that diverge.
GZ equals to.
GC, okay, but let's say all these equations require some diverging coupling constant, right? Require that some coupling constant is diverging. So it's reasonable to assume that when delta t square effects at the order delta t square become a reasonable assumption to say that the free part of the Hamiltonians are irrelevant with respect to the V. If you want, yeah. If you want, I would say, no, I mean, I don't have any other comment. The point is that, let's say, the reason for that was that V is much stronger than H. And indeed, in the delta t equal to 0 limit, V is diverging because the coupling constant is diverging. So it becomes reasonable to say that it's a meaningful expansion.
But HS
doesn't have it. No, wait. Okay. Sorry. Maybe there was a confusing point. what I call it HS, no, I mean HS branch. I was the one that was coming, was coming from V. And exactly, was the lamp shift. So it was coming from V, but was reabsorbed because it was unitary. But let's say the yesterday I was called them H0, that were the free part of the Hamiltonians that are untouched. They don't diverge in any sense. What is diverging is the coupling between the two that then generate a lamp shift. So generate, let's say, a unitary evolution, but it's still in V. You can check in the computation and you get convinced. Questions? Okay, so see you in half an hour, more or less. And yeah, the last part will be to discuss how, starting from a physical, let's say, open system, how to get a collisional description, such that, let's say, we close the loop. Here we saw how from the collisional to go to some reasonable equation, and then we will see how from a reasonable model we go to the collision.
Yes, depende of time. You get into these Hamiltonian tablets, like a time dependent Hamiltonian.
Yeah.
So it's like.
Well, no. The dimension might have what you.
Yeah.
So-
No, but I mean, if you go, if you don't you start like atom and a light, you get like this Hamiltonian. Yeah, so like my question is, choosing these to depend on time.